The first part of Quiz 1 is talking about chemical reaction equations, which is found in section 7.1 in your textbook. Throughout this entire unit, we are going to make 4 assumptions about reactions. This is throughout the entire stoichiometry, and it's anytime we're talking about any sort of chemical reaction equation. Assumption number 1 is that chemical reactions will be spontaneous. That means that reactions are going to occur without adding any energy. Assumption number 2 is that the reactions will occur fast. That means that the reaction is going to be able to occur within a reasonable amount of time, and that we can measure the time that that reaction occurs within. The third one is that they will be quantitative. Quantitative means that the reaction is going to completely use up one of the reactants, which means that the reaction is going to be essentially complete, more than 99%. The fourth assumption is that it will be stoichiometric. And stoichiometric means that we are able to compare the products and the reactants using simple whole number ratios. And that's the coefficients that we use to balance our chemical equation. When we're talking about chemical reaction equations, we're going to discuss 3 different types. The first one is the type that you've been using since grade 10. That's your complete balanced chemical equation. It can also sometimes be called a molecular equation because what we're putting into it are the molecules. The second type that we're going to introduce today is called a complete ionic equation, which means we're breaking up anything that is able to break up into ions in solution. The third type, that is what we're going to be talking about today, is a net ionic equation. A net ionic equation is only going to include the reacting entities, and it's going to omit anything that doesn't change. When we're writing a net ionic equation, we're always going to do the same 4 steps. First step is we're going to write a balanced chemical equation, which again is the same equation that you've been writing since grade 10, also known as a molecular equation. Your second step is you're going to dissociate anything that is able to dissociate, which means for any ionic compound or base, you're going to be looking at your solubility table, and if it isn't going to be soluble in water, it means you're going to dissociate it. You're also going to ionize any strong acid, which means you have to think about what your 6 strong acids are, and if it's a strong acid, it will ionize, meaning break up into its ions when it goes into water. Your third step is you're going to cancel out anything that is exactly identical, which means it has the same state, it has the same ion charge that appears on both the reactant and the product side. These identical entities are known as spectator ions because they're not taking place in the reaction. They're still present in the reaction, but they're watching it happen, and they're spectators just like a spectator at a football game. Your last step is to write your net ionic equation, which means you're writing down anything that is changing in the reaction, and you're reducing any coefficients if you are able to. We're now going to go through those 4 steps in this example. So the question that you would get is right here at the top, write the net ionic equation for the reaction of aqueous barium chloride and aqueous sodium sulfate. It says refer to the solubility table, meaning that you're going to need to make sure you know what is going to be aqueous and what is going to be solid in your products. Your first step is to write your complete chemical equation or your complete molecular equation. So in the reaction, it says in the question, it says barium chloride, which we have here on the left, and we have aqueous sodium sulfate. Then what we're doing, this is a double replacement reaction, which means your barium, which was your positive ion, is going to match up with your sulfate, which was your negative ion. And in your second product, you're going to have sodium and chloride. We're checking the solubility table, which is why our barium sulfate here has gotten a state of solid. We need to make sure that this is balanced, and to balance it, we put a 2. That's our coefficient in front of the NaCl. It's very important that we pay careful attention to our states in our complete chemical equation because our states are what is going to dictate our second step. So in our second step, anything that had a state of aqueous in our complete chemical equation, it's going to be able to break up into its ions. So if it was an ionic compound like BaCl or Na2SO4, or NaCl with an aqueous state, that means it's going to be able to dissociate. Alternatively, if you had a base that was aqueous or a strong acid that was aqueous, they would be able to dissociate or ionize respectively. So our barium chloride is going to dissociate into our barium ion and 2 chloride ions, what you will notice is up here we had Cl2, which means we're going to get 2 chloride ions. Our Na2SO4 is going to dissociate into our sodium ion and our sulfate ion. And again, notice that up here we had 2 sodiums, which means that we get 2 sodium ions. Our barium sulfate was a solid, which means this solid up here is not going to change when you write it down again as a solid. And then up here, NaCl is going to break up into 2Na and 2Cl. And the reason that we have 2 of both of those is because we had a coefficient of a 2 in our first example. This equation is known as our complete ionic equation because everything is breaking up into ions that is possible to break up into ions. The only thing that is not broken up into ions, which is a solid, and that's because it's not able to break up into ions. Our third step, what I've done here is I've written down the complete ionic equation again, and I need to cancel spectator ions. Notice up here in the top box, it says when canceling spectator ions, they must be identical in every way. The chemical amount, the form, so atom, ion, or molecule, and the state has to be identical. So what we can cancel out here, we can see on the left-hand side we have 2 chloride ions, and on the right-hand side we have 2 chloride ions. And we can also cancel out our sodium ions, because on the left-hand side we have 2 sodium ions, and on the right-hand side we have 2 sodium ions. Everything that I've crossed out in red here, we can call them our spectator ions, which again are ions that are present but do not take part in a reaction. That means that they're not changing. Our last step is to write down our net ionic equation. And our net ionic equation is we're writing down anything that was not canceled out. So we're writing down everything except for the spectator ions. That means our barium and sulfate ions reacted together to produce a solid precipitate, which was barium sulfate. So these transfer into our net ionic equation, which means this is the reaction that is happening. You need to be able to give me all 3 of those types of reactions and show me these 4 steps. So again, we have complete chemical equation, we have complete ionic equation, and we have net ionic equation. You also need to be able to talk to me about what the spectator ions would be in a reaction. This is another example. We're going to do the same thing. It says write the net ionic equation for the reaction of zinc metal and aqueous copper 2 sulfate. Again, refer to the solubility table. So our first reaction, our chemical or molecular equation, that's our complete chemical or molecular equation, is going to be zinc metal, which is a solid, and aqueous copper 2 sulfate. And it told us it was aqueous. This is a single replacement reaction, which means that what we are going to get is copper metal out and zinc sulfate. We're checking our states very carefully in this reaction because our states are what will dictate our complete ionic equation in the next step. In the next step, what we're doing, this is step number 2, is we're making a complete ionic equation by breaking up anything that is able to either dissociate or ionize, which means anything with a state of aqueous. Our CuSO4, our copper 2 sulfate, is able to break up into copper 2 and our sulfate ion. And our zinc sulfate is able to break up into zinc ion and sulfate ion. Solid zinc and solid copper they're solids, which means they're not able to dissociate in water. So this is our complete ionic equation. Our third step is we need to cancel out anything that is the same on either side, which means they're not changing. And again, they're known as spectator ions. So what you can see on the left, we have SO42 minus aqueous, and on the right we also have SO42 minus aqueous, which means our spectator ion in this example is sulfate. Our last step here is to write down anything that did change in the reaction, which means that we have zinc solid plus copper 2 plus ion goes to copper solid and zinc 2 plus ion, and that's what's known as our net ionic equation. Another example, same question, is write the net ionic equation. Here what we have is we have hydrochloric acid and barium hydroxide reacting together. Hydrochloric acid is one of our 6 strong acids, and barium hydroxide is a strong base. What we're doing here is we have a neutralization reaction, which is also a double replacement reaction, and we're making water. So 2HOH, we could also say that that's 2H2O. Up here you can see for entities involving strong acids, although in our acids and bases unit we talked about we're actually making hydronium. In this unit, for convenience sake, we're going to use H+, which means we're going to be making water. It makes our reactions a lot simpler to deal with. Again, we have to be very careful in our first reaction to make sure that we get our states down properly. In our second reaction, in order to make our complete ionic equation, we are going to dissociate or ionize anything that has a state of aqueous. Our HCl is a strong acid, which means it is going to ionize more than 99% into our hydrogen and our chloride ion. Our barium hydroxide is a strong base, and it will dissociate into its ions. And our barium chloride is an ionic compound with an aqueous subscript, meaning that it is soluble in water, and it's going to dissociate into barium and chloride. Because water is a liquid, it is not going to dissociate or ionize in water, and that means that it is going to stay as H2O, which is a liquid. Again, notice that in our first equation, we have balanced it. And because we've balanced it, we are going to take our coefficients, and we're going to end up with 2 hydrogens, 2 chlorides. Because of the 2 beside the hydroxide, we end up with 2 hydroxides. And then because of our 2 beside our chloride, we end up with 2 chlorides. It's essential that you're balancing your complete ionic equation as well. In our third equation here, what we're doing is we're canceling out our spectator ions. So our spectator ions here, we have 2 chloride ions on the left, 2 chloride ions on the right, barium 2+ on the left, and barium 2+ on the right. And those 4 things that I just crossed out, those are our spectator ions, which means they're not changing in the reaction. Our net ionic equation from this would be 2H plus 2OH minus goes to 2H2O. However, because they're all 2's, we are going to reduce that, and we're going to end up with H plus goes to plus OH minus goes to water. At this stage, although we're not going to do calculations with this yet, it's important to understand that we have something called a limiting and an excess reagent in whichever reaction we have. An example of how we can talk about this is if we're talking about hot dogs. If I wanted to make hot dogs, and what I had in front of me was I had 3 wieners and I had 10 buns, how many hot dogs could you make? Well, for every hot dog, you're going to need a wiener and you are going to need a bun. So if I only have 3 wieners, that means I am only going to be able to make 3 hot dogs. So from this example, I can talk about what a limiting reagent is. A limiting reagent is the reactant whose entities are completely consumed in the reaction. What that means is that the reaction is actually going to stop when all of that reactant is used up and none remains. So if we think back to our hot dog example, the limiting reagent here would have been the wiener, because as soon as we ran out of wieners, we were not able to make any more hot dogs. When we think about an excess reactant, that's the reactant whose entities are present in surplus. What that means is that you're going to have some left over when the reaction ends. An excess reactant is required in order to make sure that the reagent, the other thing, is going to be the limiting reagent. If we didn't have an extra amount of buns, then we couldn't have made 3 hot dogs in the first place. So in this example, if I asked you how many of the excess reagent are left over, you could say, okay, well, I started with 10 buns. I was able to use 3 of them because I made 3 hot dogs. So I could say that 10 is what I started with, and I was able to use 3 of them, which means I am going to end up left over with 7 buns in excess. Your demands for this section are on your demand sheet. However, if you want any extra practice, there's a net ionic equations worksheet in the stoichiometry extra practice folder. As you go through this unit, the stoichiometry extra practice folder has a lot of extra examples if you're finding that you would like some more practice.